Okay, thank you very much for the introduction. Yes, my name is Mladen Vukovic. I'm a senior advisor in the Environment and Business Directorate of the Environment Agency. And I'm grateful for this opportunity to possibly focus more on the climate change policies that are implemented in the UK and not as much on our role in administering and regulating these schemes because Chris has done quite a good job on that, and it is important to highlight that there are quite a number of directorates and teams that are involved in our regulating any scheme. So if I could ask for the next slide, please. So as a regulator, I think, and this includes our devolved regulators in Scotland, Wales, Northern Ireland, and offshore, I think our role is really quite a generic one. You know, we have to onboard our participants to the relevant scheme. We have to provide guidance and a help desk, ensure they comply with their obligations. We review and audit reports, undertake site visits, and we take any enforcement action for non-compliances with their obligations. We also provide technical support and report on the implementation of the schemes we regulate to our sponsoring government bodies, DEFRA, BEIS, and DFT. Next slide, please. Now, this is a bit of a busy slide. However, I have grouped the relevant climate change policies based on whether the reporting and regulation is at an organizational or site level. The first three on the slide, CRC, ESOS, and CCAs, they incentivize energy efficiency at an aggregated level to achieve the associated reduction in greenhouse gas emissions. Now, they use different drivers to achieve this, whether it's through financial incentives or raising awareness through reporting and internal audits, but all have the assessment of energy consumption in common and cover thousands of participants in numerous sectors. And I've included some headline figures in the slide there. F-gases and ODS regulation and the phase down, on the other hand, is through a quota system, which sets out how much businesses can import and place on the market in the EU. And as shown here, the phase down should reduce the availability of HFCs by 79% by 2030 compared to a baseline of 2019 to 2012. Now, we are the regulator, and by we I mean the Environment Agency is the regulator for England, and we expect to administer the quota allocation for the whole of the UK next year once we've left the European Union. If I could ask for the next slide, please. Now, as opposed to the previous policies, these are site-based. Now, I don't know how much you've heard of all of these climate change policies, but the EU ETS is a Europe-wide cap and trade scheme, and it has been running since 2005. It covers about 45% of all UK and EU emissions from very large energy-intensive industry and aviation. Now, as I said, this is site aircraft-based, and participants are required to monitor, report, and most importantly, independently verify their greenhouse gas emissions. Participants are then required to annually surrender allowances that equal their verified emissions, where one allowance equals 1 ton of CO2. And EU ETS participants are issued a number of free allowances based on sector benchmarks and the risk of carbon leakage. They can also purchase them through auctions, traders, and participants on the carbon market. Electricity producers get no free allowances, that is important to note, and small emitters and hospitals that have opted out of the EU ETS have, instead of a surrender obligation, they have emission targets instead. They can also self-verify their emissions. We audit those reports, and they pay a penalty for every ton of CO2 above their target. Now, the emissions in the UK under the current phase of ETS have reduced our annual emissions by 106 million tons of CO2 compared to 2013. And the penalties for not surrendering sufficient allowances are quite steep. As you can see there, 100 euros per ton. Now, where the EU ETS for aviation applies to flights just between European Economic Area airports, CORSIA, on the other hand, applies to all international flights between participating states. Now, this is a brand new global scheme which aims to achieve carbon neutral growth in international civil aviation from 21 onwards by offsetting emissions above their 2019 baseline levels. Now, this scheme is built on the same monitoring, reporting, and verification principles as the EU ETS. Now, just to relate, for example, CORSIA to COVID, initially the baseline for CORSIA was supposed to be the average of 2019 and 2020 emissions. However, due to the very significant impact of COVID on the airline industry and 2020 emissions, it has been agreed that only 2019 emissions will be used as a baseline. If I could ask for the next slide, please. Okay, thank you. Now, with many thanks to my colleague, David, I will not even pretend I'm an expert on landfills or methane emissions. I will hopefully provide some clarity on this topic as well, which should feed nicely into the case study being presented later. Now, this slide shows the number and type of landfills that we regulate and the number of historic, non-permitted, unregulated landfills. Now, according to the National Atmospheric Emissions Inventory data from 2018, it shows that UK methane emissions have reduced by 61% since 1990. And if you look at the bottom left graph, in that same period, emissions from the waste sector, which are made up largely of methane emissions from landfill sites, has reduced by 71%. And this reduction actually accounts for 56% of the total UK methane emissions reduction since 1990. The pie chart to the right shows the distribution between sectors where methane emissions from landfills account for 37 of the UK's methane emissions, with agriculture and energy being the other significant sectors. Now, landfill methane emissions are modeled using a package called MELMOD, which calculates the methane emissions based on the methane generated by waste and then deducts the quantities collected and combusted, as well as the proportion that is oxidized in the landfill surface before emission. MELMOD also takes into account the contribution from old historic landfill sites, older and closed permitted sites, and modern operational landfills. It applies certain attributes to each type of landfill to reflect how landfilling practice and gas management have evolved over time. Next slide, please. Thank you. Now, the EA and DEFRA have over recent years started to look at methods to quantify the methane emissions from landfill sites by measuring the emissions in order to improve our confidence in the greenhouse gas inventory reporting, as well as a regulatory tool to reduce methane emissions. Now, trial surveys have been carried out using the DIAL LiDAR system, propane tracer gas measurements, and aerial measurements with drones. And this was undertaken at non-hazardous landfills, which will produce the most methane. The work so far has indicated that operational landfills are the largest emitters of methane, with around 70% of the emissions coming from uncapped operational phase of the landfill. As a rough guide, operational landfills emit between 300 and 600 kilograms of methane per hour, whereas closed landfills with landfill gas collection systems emit an estimated 30 to 60 kilograms of methane per hour. Now, if you look at the diagram, this can be illustrated by the plan of surface methane concentrations. Now, these were obtained by a walkover using a tunable diode laser instrument, and the green areas are restored landfill and have a surface concentration of approximately 10 parts per million methane, whereas the brighter colors show increasing concentrations, with the area in the bottom right being the operational area. The site was collecting 84% of the gas generated for use in engines. However, the emissions were measured at 340 kilograms per hour methane, mainly from that operational area in the bottom right. Next slide, please. That was it from me. Thank you for your patience, and I hope this whistle-stop tour wasn't too quick, and the right amount of information was conveyed. So I welcome any questions.
Thank you for the opportunity to speak at the meeting today. I am going to just give a few examples of how we can use satellite observations of tropospheric column NO2 for kind of UK source detection, and how this might potentially be useful for like the Environment Agency in the future. So I've been working quite closely with Andrew Brown on this with the summer student. Kind of sources of pollution in the UK. So the two instruments that thank you. So the satellite missions that I've been looking at are the ozone monitoring instrument and the tropospheric monitoring instrument. So Hartman gave a quick overview of TROP-OMI. OMI itself is on a NASA satellite launched in 2004, has an overpass time of about 13:45 local time. It's nadir viewing with a spatial footprint of 13 kilometers by 24 kilometers. So that's when it's viewing in nadir. And it has a spectral range in the UV vis of about 270 to 500 nanometers. TROP-OMI was launched in 2017. It has a similar overpass time to OMI, but it has a much finer spatial footprint at nadir of about 7 by 7 kilometers, but that can go down to about 7 by 3, I think, depending on the part of the spectrum you're looking at. And it can look in the UV visible, near infrared, and shortwave infrared. So the first kind of example I want to show is that whereas, like, surface monitoring sites kind of are very useful telling you what the surface, they give you limited spatial coverage. So this is where satellite data is very useful. So this is like an 11-year average seasonal cycle from OMI tropospheric column. And what you can clearly see is that we've got very detailed UK coverage where you can pick out kind of clear city sources. So like London, you've got Manchester, Liverpool, Birmingham, and you can see the clear seasonality with kind of large concentrations in winter, and then smaller as you go through summer due to the photochemistry, and then going back to higher values in the autumn. And when we can build up these sort of spatial maps and time series, we can actually start to look at how kind of city scale and like source scale NO2 has changed over time, using kind of a non-linear least squares fit regression, which kind of takes us to the seasonal and linear components of kind of temporal variation. We can start to look at trends. So we're really interested in like this kind of B term here, which is the linear trend, and this is the trend shown over so this is the annual trend over 11 years. And what we can clearly see is that across the UK there has been kind of large scale reductions in NO2 in many of the kind of the urban regions. What I will say is that I've not kind of put if these trends are significant or not on here, because on a pixel by pixel basis it can be very noisy. So we need to ideally kind of look at regions to reduce the satellite noise, kind of as Hartman was saying, that clouds is a problem, as is just the general sampling uncertainty. So what we need to do is kind of average over regions, bring down kind of the random error component, and then we can start to get kind of robust trends above the noise of the instrument. And this is sort of shown in these examples here, where kind of looking at London, Manchester, Birmingham, and probably more interestingly for the EA DRAX power. So kind of like this 11-year time series, we saw that there's been a kind of significant decrease in all of these locations in tropospheric NO2, shown by kind of the blue line shows the linear trend here. And interestingly for DRAX, we can see actually there's been quite a large scale decrease over the time period, so it's nearly comparable to London in terms of the trend size over this time period. When I say DRAX, I should say that this is kind of like a regional average over centered on DRAX, but does include like the Ferrybridge and Eggborough power stations as well. So we can use kind of like OMI to kind of look at the kind of larger scale regional patterns and how they're changing over time. Going on to looking at DRAX itself, we were trying to see if, I've taken a region before and averaged over it, but we wanted to see if like OMI could identify DRAX. So DRAX is like the biggest power station in the UK for emissions, and looking at this bottom panel here, you can see that DRAX, Eggborough and Ferrybridge, which are all very close to each other in kind of North Yorkshire. You can see that, it's the blue, red and green plots here. So this is kind of a list of the top 100 point source emissions for 2012 for NOx, and we can see that, DRAX is the highest by a long way, followed by the two other power stations, I think at 8th and 9th. So there is kind of a large emission source here, kind of shown in this map. So initially when we looked at the map, we weren't sure what this was. So we kind of thought, well, we know the power stations there. Could they be driving this kind of hotspot? So I've zoomed in on the region in the white box, and I've then given the kind of 7-year average here for 2005 to 2011. And you can sort of see that there is quite a lot of noise in the data, but you can see that the plus DRAX, there is kind of quite high NO2 values. So we thought, well, you've got a lot of other sources like kind of Hull downwind, you've got Leeds nearby, the M62 and other things. So what we thought we'd do is we would sample the pollution under kind of low and high wind speeds. So we took kind of like the surface sites, got the average wind speed and set kind of a threshold if it was above or below 2.5 meters per second. And what you can see is when you have like the high winds, you can see there's this sort of downwind transport of pollution from DRAX and Leeds and Hull. Because climatologically, you've got the prevailing southwesterly winds, hence why you've got the kind of the transport in this direction. But actually, when you look at low winds, so you've now kind of taken the transport of pollution sources to in situ out of the equation here to a degree. And you can actually see that when you've got low winds, the highest pollution is over DRAX and Eggborough. So this kind of quite strongly infers that actually this kind of UK pollution hotspot is coming from the power stations themselves. This is then where TropOMI comes in and can be very useful, because whereas OMI we had quite coarse, broad signals, you can now start to get much higher resolution, detailed kind of pictures of it. So this is just a kind of quick example of some sources from like southwest England / Wales, and this was just kind of using summer data of 2018. And what you can see is that OMI itself would not be able to detect these sources very clearly, whereas here like Bristol, Cardiff and like Port Talbot, for instance, are all very visible by TropOMI and detected. You've already got Newport here as well. So we're now starting to see sources that were previously undetectable from OMI, and they correlate very nicely with the NAEl. So this is National Atmospheric Emission Inventory, bottom-up emissions. And what we can see spatially, they look very consistent, which is good. So we can now start to potentially use like the satellite data to derive kind of top-down emission inventories for evaluation of the bottom-up inventory. So moving on to DRAX, this is now the TropOMI data over 2 years. And we had a summer student called Katie Wade, and working with Andrew Brown, who's on secondment, the Environment Agency. We were looking at kind of some big sources, point sources. So we had DRAX. I see these plots kind of when we kind of look at the DRAX, the average NO2 over DRAX for different wind directions, we can actually start to see examples of these plumes. So we can nicely see that under the northerly winds, we can see there's this downwind plume from DRAX. I mean, there are other sources as well here, but we can quite nicely see some enhancement downwind of the source, some of the black dot here. And then again, from like the northwesterly flow, you can see that, you've got Drax here, and then we've got some evidence of some plumes here. We have quite a few different examples of this, which we're going to try and kind of write up into a report for the EA. But just kind of showing the nice examples of tropomi, and now we're starting to get to the resolution where we can really see kind of high resolution point sources. This is a slight aside, but I thought it'd be a nice thing to show. This was kind of showing how you can use tropomi carbon monoxide data to detect the Saddleworth Moor fires that we had in the summer of 2018. So this westward propagation of the winds and the smoke plume, these are actually being started to be observed by kind of these much higher resolution instruments such as tropomi. And this is just an example of a kind of a time lapse of the data. So you can see that over Saddleworth Moor on the 25th of June 2018, we can see that you've got some carbon monoxide starting from the fires, and then you've got this big kind of signal. And then when you've got in the kind of the mid-troposphere, you've got these kind of westerly or easterly winds, sorry. You can see this westward propagation of the plume away over like Manchester out towards Hull. And you can see that then you had like the Winter Hill fires as well that started on the 30th of June. So, and just to say that the black dots sort of represent fire registered power, so it's essentially another metric for detecting where the fires are. So you can see the plumes nicely starting where the fires have been detected. So I thought that was just a nice quick example to show of what tropomi can do from like an air quality point of view. So yeah, that kind of covers the majority of the points I wanted to make. So I was a bit quicker than I was expecting, but yeah, so there is a few other examples as well, kind of where we can use something like satellite data to evaluate like the Met Office air quality model, which provides the air quality forecasts. You can use aerosol data sets to observe like bonfire night pollution, and sort of what's similar to what Hartman was saying, like you can use the land weather types to look at long-range transport of NO2 plumes, or the accumulation of NO2 over point sources in the city scale sources in the UK.
I've been delivering a project investigating how the EA could potentially use satellite-based measurements of air quality and greenhouse gases. And this talk described one part of this work, a short case study looking at using the IARS instrument to determine seasonal and long-term trends in measured ammonia in the UK. And the work I'm about to present has been delivered without the efforts of Ty Haywood in the EA's geomatics team. Ty developed the code to process the IARS data products and produce the results derived from the satellite data that are shown in this presentation. I'll start with a few words about ammonia, which in the UK is predominantly emitted from agricultural processes. These accounted for 88% of all ammonia emissions in 2016 and 87% in 2018. Two areas of concern for ammonia are that it first damages sensitive habitats through a process of nitrogen deposition, resulting in a decrease in biodiversity. This is a widespread problem in the UK, as over 60% of sensitive habitats are exposed to more nitrogen than they can effectively cope with. Secondly, ammonia reacts in the atmosphere to produce particulate matter, which have a range of significant health impacts, including respiratory diseases. There is currently a major focus on ammonia as a pollutant of concern because emissions of ammonia have fallen at a much slower rate in the past few decades than that of other pollutants. This is shown by the chart on the left-hand part of the slide. Ammonia emissions have only decreased by 10% since 2007 and are in fact rising again. They've risen by 2% between 2015 and 2018. This means that the UK is in real danger of missing its target set by the National Emission Ceiling Directive of reducing emissions of ammonia by 2020 by 8% compared to a 2005 baseline. A further breakdown on the agricultural sources of ammonia is shown on the right-hand side of this slide, with cattle being the source for approximately half of the UK's agricultural ammonia emissions, followed by fertiliser applications, poultry and pig farming. And also just to mention policy and regulation. The government's 25-year environment plan, published in 2018, committed, amongst other things, to publish a clean air strategy to set out how to work towards the UK's legally binding ceilings on UK emissions of air pollution. This was published in 2019 and set out the actions shown here to reduce emissions from farming. Of particular note for regulators such as the Environment Agency is the intention to extend the permitting of farming to the dairy and intensive beef farming sectors. Because as shown in the previous slides, these sectors are responsible for significantly more ammonia emissions than the pig and poultry farming sectors that are currently regulated. So moving on now to our case study, the three questions we attempted to address are shown here. Firstly, can monthly, seasonal or annual trends in ammonia over the UK be identified? Secondly, can areas of the UK with large recent increases in measured ammonia be identified? And thirdly, can ammonia satellite data alone identify regulated activity in the UK? And we use the IASI instrument for our study. IASI is a passive remote sensing instrument operating in downward viewing geometry, which is in orbit on 3 METOP satellites. For our study, we used data from the IASI instrument on the METOP satellite, as this gave the longest data coverage to interrogate. METOP is in a sun-synchronous orbit with 2 overpasses per day, and the pixel size is a minimum of 12 kilometres by 12 kilometres at the nadir, up to a maximum of 20 kilometres by 39 kilometres at the outermost viewing angle of 48 degrees. The instrument performs measurements in the infrared region, which importantly means that no measurements are possible when the optical path is obscured by cloud. Some detail of how we process the IASI data is shown in this slide. I won't go into this in too much detail, but some of the key points are that we did all of the work in-house, developing a new capability from scratch. This was a steep learning curve and involved processing a large amount of data. We only use the morning measurement from each day due to it being of a higher sensitivity than the afternoon measurement. We used a gridded approach and a grid of 0.25 degrees by 0.25 degrees, assigning the measurement to the grid box based on the location of the centre of the particular measurement. And we removed measurements with more than 10% cloud coverage. We should also thank Martin van Dam and colleagues at Brussels University, who very kindly provided us with the level 2 ammonia product. And we also had very useful discussions with Colin Borer from Birmingham University and Eloise Murray, now at UCL, and Eloise is giving the presentation immediately after mine. Some things that we haven't done is converted total column ammonia in molecules per square centimetre into near surface concentrations over micrograms per cubic metre, used oversampling to produce gridded products with sub-pixel resolution, and we haven't propagated the uncertainties from level 2 product to the gridded level 3 products. So moving on to some results from our case study and addressing the first question, can monthly, seasonal or annual trends in ammonia over the UK be identified? This slide shows the annual median total column ammonia measured over the UK in each year from 2008 to 2018. And although it at first appears that the measured ammonia might be increasing over the last few years, any consistent trend is very difficult to identify, at least partially because each annual average is comprised of only a limited number of measurements, somewhere between about 35 and 95. And this non-representative sampling throughout the year results in non-systematic biases in the annual averages. This next slide shows the seasonal average results using all data from 2008 to 2018. Here there is a clear seasonal trend with the highest levels of ammonia measured in the spring and summer and the lowest in the autumn and winter. And a similar trend can be observed in the monthly data, again with the highest levels of ammonia observed in the spring months, closely followed by the summer months, and then the lowest levels of ammonia shown in the winter periods. We then undertook an indicative comparison of these results with data from the UK Ammonia Monitoring Network. The Ammonia Monitoring Network currently comprises 96 monitoring stations around the UK, which use either active delta samplers or passive alpha samplers. And even though this isn't a full like-for-like comparison, as, for example, the spatial coverage of the ammonia monitoring stations isn't representative of the average UK ammonia concentrations, and a number of small assumptions were made during the processing of the data, the volume of the data covering 11 years of measurement still makes the comparison a worthwhile one. And as you can see from this slide, just even observing it by eye, the trends in seasonal and monthly IASI data shown in the images at the bottom of the slide are replicated by the average ammonia concentrations calculated from the Ammonia Monitoring Network in the plots above. And taking the seasonal data on the left-hand side as an example, there is a clear trend of decreasing ammonia in both data sets as one progresses through the seasons. Attempting to quantify this further, these plots show each of the calculated normalized annual, seasonal and monthly data plotted as Ammonia Monitoring Network average data on the x-axis against IASI average data on the y-axis. And although little correlation is observed from the annual data, the seasonal data shows a strong agreement between the two sets of data, as shown by the small deviation from the line, and the large seasonal variation, as shown by the length of the line. The monthly data shows a strong monthly trend, but a slightly less strong agreement between the data sets. Moving on briefly to the second of our questions, can areas of the UK with recent large increases in measured ammonia be identified? We compared the average IASI measured total column ammonia during the period 2013 to 2018 to that during the period 2008 to 2013. These 6-year averages was chosen to try and reduce some inconsistencies in the annual average data discussed earlier. The image shows the relative differences in measured total column ammonia relative to the UK and Ireland land average increase over the same period. And from the map, a small number of predominantly red and orange areas can be seen, which correspond to above UK and Ireland average increases. The area highlighted in the box on the right-hand side shows a particularly large increase corresponding approximately to the Powys area of Wales and the Cheshire and Shropshire parts of England, where there has been significantly recent increases in intensive agriculture. So to conclude by addressing our 3 questions, firstly, can monthly, annual or seasonal trends in ammonia over the UK be identified? For seasonal and monthly data, yes, the trends seem to be very clear, but note that we have not considered the uncertainty of the measurement in the study. For annual data, no, the sparse data coverage makes any trend observation very challenging. For the second question, can areas of the UK with recent large increases in measured ammonia be identified? We have found some evidence of this. We found increases in measured ammonia over areas of the UK with large increases in intensive agricultural activity, for instance, Powys, Shropshire and Cheshire. And finally, can ammonia satellite data alone identify regulated activity in the UK? This hasn't specifically been discussed in this presentation, but the simple answer at the moment is no. The data is too sparse, the spatial resolution is too large, and measurements over the UK are not visually sensitive. This is coupled with the fact that there is a lack of large ammonia point sources over the UK. It is worth noting, however, that ammonia point sources have been identified outside the UK using IASI data by other research groups, but these point sources are larger and less dispersed than those in the UK. The sensitivity of the measurement is higher, and temporal averaging with oversampling and supersampling, sometimes with wind rotation, has also been used. And finally, just to thank all of the people listed on this slide, some of whom I have mentioned before, without whom this work wouldn't have been possible. And of course, thank you very much for listening.
Thanks, Andrew, for setting up really nicely a background around ammonia in the UK, and also a description of the IASI instrument. So that sort of section where we have some overlap, I'll just breeze over. But just to give context, the intention behind this presentation is to share results of deriving ammonia emissions from satellite observations of ammonia concentrations, making use of a chemical transport model. And just to acknowledge that this research is funded by DEFRA, I'm sharing preliminary results in this presentation, and the results that I share are largely due to data analysis by my postdoc, Alok Pandey. What I'm showing here, Andrew has already covered, so I won't go into too much detail, but the plot on the left shows quite nicely a success story of reductions in emissions of many air pollutants, non-methane volatile organic compounds, sulfur dioxide, primary PM2.5, and also NOx. But ammonia deviates from the success story. It's shown that there's been a decline due to decline in ammonia from vehicles, but there's been a recent uptick in ammonia, and I'm showing a slightly older version of this to what Andrew showed. There is a slight downturn in 2018, but in general, ammonia hasn't changed in the same way that the other air pollutant precursors have changed. The plot on the right shows the spatial distribution of ammonia emissions according to the UK National Atmospheric Emission Inventory. These are gridded to 1 kilometer resolution. What I'm showing here is for 2018, and we only are given an annual emissions from the NAEl. The hotspots are largely located over Northern Ireland and at the border between Wales and England. And there are many challenges in deriving an emission inventory like this. We're reliant on activity factors, mostly from agricultural activity, and we're also reliant on relatively static emission factors in putting together what I'm calling a bottom-up emission inventory. And then on the next slide, what I'm showing is that there's also a complex interaction between ammonia and other air pollutant emissions. And so that's shown on the left-hand side. Ammonia partitions to the aerosol phase to form ammonium and then goes on to contribute to PM2.5 mass. So very small particles that we breathe deep into our lungs and have adverse effects on health. And this complex partitioning process is dependent on emissions of NOx that lead to formation of nitric acid that then form aerosol phase nitrate, but also SO2 emissions that form sulfate that allow for the partitioning of ammonia, which acts as an acid buffer. I think the first author of this result that I'm showing on the right is on this call, so he would probably do a much better job at demonstrating the results from his work. But what this work that he did showed is that the air quality policies targeting ammonia emissions have the potential to have larger and more widespread effect on PM2.5. So what the plot is showing is the base PM2.5 concentrations in the top left, and then alongside that is what happens if to PM2.5 for 30% reduction of different precursors that contribute to PM2.5. And the top middle plot is for ammonia, showing quite nicely the benefits of targeting ammonia emissions, largely from agriculture. And then if you progress to the next slide, the focus here is really on a top-down perspective. Can we take observations of ammonia from satellites, apply a chemical transport model and convert this to ammonia emissions, and then use that to evaluate the NAEl? The The approach that we use to grid the data is this oversampling technique that's been mentioned a few times. And what I'm showing here is a very crude representation of this process. But effectively what happens is that a fixed latitude-longitude grid, where I've chosen 0.1 degrees by 0.1 degrees, or about 10 kilometers, depending on where you are in the world, is this area-weighted and uncertainty-weighted regridding of IASI pixels, where the IASI pixels are at 12 kilometers or 0.12 degrees directly below the satellite or at nadir, and then these degrade in spatial resolution as you move further out to the edges of the swath to about 39 kilometers. So what we're doing is really gaining more spatial information, making use of the fact that IASI doesn't always observe the same location with each orbital overpass. But there is a trade-off. We lose temporal resolution, so I won't be able to show you annual monthly averages from IASI. What I will be showing you is multi-year monthly averages, because I need to use a lot of data to generate reliable gridded IASI ammonia. And then just to acknowledge that the oversampling code that I'm using is published by Lejeune and others in a 2017 publication, where they applied it to observations of formaldehyde to derive higher resolution surface concentrations of formaldehyde in the US. And then if you can progress to the next slide. What I'm showing here are the seasonal averages. So you've seen a flavor of this from Andrew as well, but here it's 0.1 degrees by 0.1 degrees and averaged over a long time period. The data is noisy in winter because we don't have a strong temperature gradient between the land surface and the atmosphere that we rely on to retrieve reliable observations of ammonia from satellite observations. This improves when we go into the season where agricultural activity is at its maximum, so March, April, May, June, July, August. And also over the ocean, the same issue exists. There's not a lot of ammonia to see in the first place, and there also isn't a big temperature gradient between the ocean surface and the overlying atmosphere. Just to acknowledge that the units here aren't the typical units that we understand or engage with when we think about air quality. We normally think about surface concentrations as micrograms per meter cubed. Here, what I'm showing is 10 to the 16 molecules per centimeter squared. And what this means is the number of ammonia molecules in a column of air from the Earth's surface all the way up to the satellite. And just to acknowledge, same with Andrew, I'm using the IASI data product that's generated by the group at ULB in Belgium. If you can go to the next slide. This just describes the general steps that are taken to go from satellite column densities of concentrations to surface emissions. And so we start with the column densities. These are oversampled, regridded. We then use a model to obtain the relationship between the concentration through the column and the emissions at the surface. And we apply that ratio to the satellite column densities to then derive surface emissions. In our case, we were interested in ammonia emissions. And this certainly isn't a new approach. This is quite extensively used, and mostly in deriving NOx emissions from tropospheric column densities of NO2, but also in deriving isoprene emissions from vegetation from satellite observations of formaldehyde, which is a high yield prompt oxidation product of isoprene. So I'm certainly not the main innovator in this approach. It's standard, but what's nice about it being standard is that it's generally quite reliable in being applied to something like ammonia, which is quite short-lived, and so will be co-located with the emission sources that lead to the enhancement in ammonia in a column of air. If you can go to the next slide, please. The model that we use to relate the column to the surface emissions is the GEOS-Chem chemical transport model. This is a 3D atmospheric chemistry transport model. And in this image, I'm just showing you the different kind of bells and whistles that are associated with this model. The model can be run globally, but also nested over specific domains to take advantage of the higher spatial resolution of the meteorology that's used to drive the model. So for this purposes, I use the European nested domain of GEOS-Chem, which is at about 25 to 30 kilometers resolution. In the model is an exhaustive list of emissions from both natural and human sources. I update the model to include the UK NAEi emissions for 2016, and then the EMEP 2016 emissions for mainland Europe. Both of these emission inventories are reported as annual values, and so I apply temporal scaling factors that are already implemented in the GEOS-Chem model to represent seasonal variability in these emissions, to represent diurnal variability in these emissions, and where it's relevant, also weekday and weekend effects in the emissions. The offline assimilated meteorology that I use is the NASA GEOS-FP meteorology, also for the same year, for 2016. And so this is from the GEOS model, and where available it also includes information from observations. And then the sort of meat and bones of the model is numerical representation of gas phase and heterogeneous chemistry, also transport of pollutants vertically and horizontally, and then importantly for PM2.5 and ammonia, dry and wet deposition, which represents a dominant loss process for those atmospheric components. And then if you can progress to the next slide. We also need to evaluate the performance of the model, and to do this we use surface observations. If we had aircraft observations that gave us information about the vertical distribution of ammonia, we would use that, but we don't have them for the UK specifically in the locations of interest and across the atmospheric profile of interest. And so in order to evaluate the GEOS-Chem model, we use surface network observations from the UK EAP network. And so what's shown in the background is the model's average of different surface components, and then in the circles is the values from the monitoring network. The reason I'm showing sulfate, nitrate, and gas phase nitric acid is because there is this dynamic relationship between these components and PM2.5. The more aerosol sulfate and aerosol nitrate we have in the atmosphere, the more ammonia partitions from the gas phase to the aerosol phase. And we find from comparison between the model and observations is that the model is reasonably representing aerosol sulfate, but is underestimating aerosol nitrate and overestimating gas phase nitric acid, which means that there's an imbalance in the formation of aerosol nitrate from gas phase nitric acid. And so if you go to the next slide, what I'm showing there is that this imbalance in nitric acid and aerosol nitrate might be due to an underestimate in the ammonia emissions in the model. And that's demonstrated by comparing the model and observations of annual mean ammonia, where we see that there is this 50% underestimate in the model, where I'm just quantifying that as a model normalized mean bias. The model doesn't do too badly at annual mean ammonium, which initially surprised me, but if I compare NHX, which is the sum of ammonia and ammonium, most of the NHX is coming from gas phase ammonia. And so in general, the model is underestimating this emission source, this ammonia emission source. And so if you go to the next slide, what we then do is that we apply this model to obtain emissions of ammonia from IASI. With this issue that, of course, there are uncertainties inherent in the model, what we haven't done yet, but we can do, is to test what the implication is of these mismatches between the model and surface observations in deriving ammonia emissions from these satellite observations. And so what you can see is similar to the pattern that you've already seen with Andrew's work, is that in January, February, October, November, December, the winter months, the cold months, there's a lot of noise in the satellite observations. It's challenging to observe or retrieve ammonia during these months. And so we get the most reliable information during the sort of agriculturally active months. So March, April, May, June, July, August, September. The numbers that are shown give you the total monthly emissions for the grids where there are IASI ammonia retrievals. And so in the next slide, what I'm showing is the NAEl ammonia emissions, or actually I might be showing the uncertainties. I'm preempting my slides, not knowing what's coming next. So what we look at here is what the size of the uncertainty is in the IASI ammonia columns. And it's sort of a story that's consistent with what we've seen before. January, February, October, November, December, the uncertainties in each grid square can be larger than 100% because of the inherent challenges in observing ammonia in these months. But this improves in particular south of Scotland in March, April, May, June, July, August, September, where the uncertainties now decrease to 20% or less. And if you can go to the next slide, what I was preemptively anticipating is that this shows the spatial distribution of the NAEl ammonia emissions. In this plot, what I'm showing is all of the NAEl ammonia emissions, not just those co-located with the IASI-derived ammonia emissions, to show that for March and September, these months collectively represent about 70% of annual NAEl ammonia emissions, which means that in the months where we can actually obtain useful information from IASI, we're capturing 70% of the ammonia emissions, at least according to the NAEl. And so it's hard to remember what the values were that I showed for the monthly emissions in the previous or 2 slides ago, but in the next slide, you'll see the comparison between the NAEl and the IASI-derived ammonia emissions. And so what this shows is that any grid squares that are blue, the NAEl is less than the IASI-derived emissions. Any grid squares that are red, the NAEl is greater than the IASI-derived emissions. For the most part, the red grid squares coincide with really large uncertainties. So in general, the NAEl is underestimating ammonia emissions according to the IASI-derived ammonia emissions. You can see that in general in the monthly emissions, that shows up as well, and it sort of escalates with each month, that by July, there's a 40 gigagram difference between the NAEl and the IASI-derived emissions. And you can also see, I've put there the numbers of the total NAEl for this time period for grid squares that coincide with IASI-derived emissions. The value is 174 gigagrams, whereas for IASI, it's 290 gigagrams. So this indicates that during these months, the NAEl is 1.6 times less than IASI. So the reported error for the NAEl ammonia emissions that I use in this work is 31%, and we still need to calculate what this uncertainty is in the IASI emissions. So similarly, we'd be able to say whether there is a statistically significant difference between the NAEl and IASI-derived emissions. And then, of course, we'll be able to interrogate specific locations where we see really large discrepancies between these 2 different emission estimates and then determine what the underlying dominant agricultural activity is in those locations where we see the largest discrepancies. And then if you go to the next slide, I think this is just the acknowledgements. So just to thank DEFRA for funding for this project, Alec Pandey for doing the bulk of the data analysis that I showed, the group that retrieves IASI ammonia, and then also Leju for providing the oversampling code, and most importantly, the really large team that maintains the very precious surface monitoring network that we rely on so heavily to validate model performance as well as satellite observations. And I hope this network sustains itself into perpetuity. And if you have any questions, you're welcome to, of course, ask me in the chat or follow up with an email. Thank you very much for your attention.